of the cell, but it hits 202. They go, right? Yeah, I was just saying to Helen that I don't plan to speak for the full hour already. It's fine. That's aiming for 25 to 12, 30 minutes, something like that.
Please introduce yourself.
Correct. Yeah, of course. Yeah, so my name's Steve, and I'm a final year PhD student of Helen Burns. And yeah, so I mean, my work is on structured population models for early atherosclerosis. So this is some work that we've been doing, over the course of the PhD at the University of Oxford. And also, I want to mention that this work is in collaboration with Professor Mary Myersgill at the University of Sydney, and also the Spatial stuff, Dr. Mike Watson at the University of New South Wales. Yeah, okay. So I think we'll just get started. So first of all, I have to tell you a bit about, what is atherosclerosis, this thing that I'm studying. So atherosclerosis is a chronic inflammatory condition of the artery wall. And the reason why we care about it is because it's the leading cause of cardiovascular disease, which in turn is the leading cause of death globally. So it's a big health problem. But what is the big picture of this disease? Basically, early on in your life, the outer layer of the artery wall becomes damaged due to disturbed blood flow. That allows these so-called LDL particles, these are your bad cholesterol particles, to infiltrate the artery wall. And these LDL particles carry on with this fatty compounds called lipids. So your artery wall ends up accumulating lipid. That triggers an immune response, which called the monocycle macrophages. So these macrophages come to the lesion, and their job is basically they go around the extracellular space and they eat up the extracellular lipid seed. And when they do that, once they do that, they try and offload it onto these HDL particles. These are your good cholesterol particles. So basically, as this disease goes on, the immune reaction gets more and more complex. More and more species get involved, and you end up with a large core of extracellular lipid on the right-hand side. This is really bad because parts with a large extracellular lipid core are vulnerable to rupturing. And when they rupture, that lipid core gets released into the bloodstream, and that's what blocks the blood and gives you a heart attack stroke. So we're really trying to working on the right-hand side of this diagram. But the focus of my modeling is on the early stages of this disease, where there isn't much actual remodeling of the artery wall at this stage, and we're just looking at the immune dynamics that are going on. So just for context, really, my PhD research for atherosclerosis consists of 4 main projects. Basically looking at the macrophage population in different levels of biological detail. So at the start, we looked at a macrophage population that was structured according to a single index L. So this index is lipid content. We were just looking at how lipid is distributed amongst the macrophage population and how that distribution changes with time. What we then did recently is we added a second index, phi, to account for macrophage phenotype. So we have a dual structured phenotype lipid model here. But the point is, both of these works are spatially homogeneous. We don't account for any spatial work in these 2 projects. What I'm working on at the moment is generating spatially resolved models. So in particular, I'm going to speak a little bit about the lipid spatial model as well, with the end goal of ending up with a fully resolved phenotype lipid spatial model. That's the aim. But with this talk, so I'm going to be dividing the time basically between these 2 projects. So phenotype lipid. This is spatially homogeneous, but there's interesting movements in the treatment of structure space that I'd like to speak about. And then I'll speak a bit about the lipid spatial modeling that I'm working on at the moment, but there's actual. So onto the phenotype lipid model. So here, this modeling was basically, we did this to address a couple of key questions. So first of all, the biologists are thinking about macrophage phenotype now as kind of spectrum from M1-like cells on one extreme and M2-like cells on the other extreme. But the mathematical modeling literature hasn't quite caught up to this, and we still reach two distinct pools of M1 cells and M2 cells. But what happens when you actually have a spectral phenotype? That wasn't known. So what are we addressing here? We want to know if, well, how phenotype and lipid content are distributed amongst macrophages. But also, are phenotype and lipid content correlates to the norm? These are the two main questions that we're trying to address here. So, in this model, you can think of the macrophages living in this two-dimensional structure. It's basically this rectangle here. On the horizontal axis, we have phenotype. So, this phenotype index phi take negative values corresponding to anti-inflammatory phenotypes and positive values corresponding to pro-inflammatory phenotypes. You also have lipid content on this vertical axis here. So macrophages basically live resolved according to phenotype and lipid content.
So just a question. So the phenotype is a continuous variable. So
it's I hesitate to say continuous because we're using a discrete structure here, but it's resolved as a spectrum. So there is one extreme in the M1 extreme macrophages. There's another extreme, which is the M2 macrophages. But we allow many steps in between.
So there is evidence that there are all these different phenotypes?
Yeah, so there's evidence of a spectrum of phenotypes between M1 and M2. That's the key thing. There is, reasonable questions about the spacing, how macrophages go in, but that there is a spectrum of something. Okay, so in this model, newly recruited cells enter this rectangle from the origin. So we assume that they have a phenotype, they're phenotypically neutral, so they're uncommitted, pi equals 0, and they enter with a minimal amount of lipid content. And they move around in this diagram in the 4 cardinal directions according to different biological processes. So first of all, macrophages can move up in this diagram, so they can increase their lipid content by taking up lipid. And we model this using the reaction on the left. So if we use mass action treatment of this reaction here, the key thing is that the L index increases by 1 as you go through this reaction. And the rate of this reaction depends on L. And it depends on L in such a way that the rate goes to 0 as you enter this upper boundary. That just stops macrophages from actually escaping this diagram. They get trapped at the top. Okay, so this is lipid uptake. Macrophages can move down by offloading lipid. So offload lipid onto these HDL particles, and the reaction will decrease the L index. Macrophages can undergo pro-inflammatory activation. So when macrophages interact with pro-inflammatory mediators, you've seen that increases their phenotype index, so it makes them more pro-inflammatory. And there's an associated reaction with that as well. And similarly, there's anti-inflammatory activation, interact with resolving mediators instead. So macrophages move around in these 4 cardinal directions according to these reactions that I just presented. So these are just the macrophage equations. If you do a full mass balance of the full model, there are many more equations that pop up. But I don't want to draw your attention to the details on the focus on the actual macrophages. So in particular, notice that, so each of these lines here, the macrophage equation corresponds to one of these. So this is uptake, this is offloading, this is pro-inflammatory. We also account for depth and integration. So these are the discrete set of equations here. What actually happens So here I run a numerical simulation. So this is what happens to the ODE system at the time it goes on. Then for two different cases here. One case uses a healthy set of parameter values where your LDL to HDL balance is healthy. And one where you have too much LDL balance to HDL. And basically you can see that for the nodes of health, first of all, lipid content. You get high lipid content in the right-hand side, phenotypes are generally more pro-inflammatory on the right-hand side in this unhealthy case. But one of the key features, so just looking at snapshots now of the unhealthy case, that distribution isn't just any distribution in space. It's a curve. It's basically a curve that's sensitive about a curve that starts from the origin. So state curve. That starts from the origin and ends somewhere in the actual interior of the space. We want to understand why this is happening, and to try and track this behavior that can. So if you actually look at the discrete set of equations, it's actually rather difficult to return any analytical segment. What we found instead to be quite productive, especially with our lipid structure modeling, is to actually consider a continuum instead of a discrete set of equations. So what we did is we made some estimates to find a continuous phenotype variable, which is pi divided by pi max, so it's about 1. Continuous phenotype, which is about 0.1. Instead of using a family of functions m by l of t, we identify that a single function n of pi as basically what you can do is in this using this identification, you can rewrite the discrete equations as a set of non-local and what you do is you can expand with respect to the small parameter epsilon, which is element to the -1, and very close. What you get is you get the peak field that was the dynamics. And this might be kind of right now because it seems like I've made one kind of impossible problem for another impossible problem. It's not exactly the same as PDEs. But if you actually rewrite this, you can put it into conservation. And what you find is that this is actually an effect in the diffusion program. And more than that, the diffusion is small because it scales with that small parameter epsilon. So at leading order, you get an advection equation. And this is something that we can actually understand. So advection is being pushed around by some kind of velocity field, and the velocity field is determined by coefficients of those terms there. And this is a picture of what that velocity field looks like. So I've done this at different snapshots in time. And the point here is that the velocity field has one key feature. It has, at every time, has a single point of zero instantaneous velocity. So what that means is that the field is always pushing macrophages towards one particular accumulation. So from this perspective, it's actually somewhat obvious as to why the distribution behaves as a curve at steady state. But these macrophages are acting as basically particles dropped into a river. They get dropped at the origin, and then they get put towards this accumulating by advection. Now, of course, the velocity field itself is determined by the extracellular environment. But again, it's unsurprising as to why the distribution actually is shaped like a curve. You can actually solve these characteristic equations at steady state. What you find is that you get a relation between phi and L. And this curve approximates the center curve of the actual two-dimensional distribution. So we use the leading order dynamics of the continuum problem to really extract some global information out of the discrete problem here. But yeah, what does this say? So it says that phenotype and lipid content are correlated according to a power law. Now you can see that the correlation is either negative or positive, or it can be either, depending on your LDL to HDL balance. On the left-hand side, for LDL to HDL, higher lipid contents are associated with smaller values of carbon. So the higher the lipid content, really well. But on the right-hand side, higher lipid contents are associated with higher values of carbon, so you're more pro-inflammatory. So you can do some extra analysis looking at the actual marginal distributions. So just integrating across phenotype and integrating across lipid contents. And long story short, what you find is that you can derive uniform asymptotic approximations of these marginal distributions. The main thing is that at that accumulation point around here, what you find is that there is an inner region of order epsilon and a half, where the function behaves as a hypergeometric function. But yes, point is, we have uniform asymptotic approximation of marginal distributions. So what I've shown here is a plot of the discrete model output, and I've compared it to the asymptotic approximation of the continuum approximation of that discrete model. And it still lines up quite well. But the point is here for this phenotype lipid modeling, that converting discrete models to continuum framework can be very useful, especially if it's the kind of natural problem. I want to bring up another problem that we have, namely that we have asymptotic solutions marginal distributions. We know this, but we don't have an asymptotic solution for two-dimensional distribution. So at steady state, and the problem is if we divide this PDE into two variables. The issue is that it's singular. It's a singular pervading problem in epsilon. So the higher order derivatives vanish as epsilon goes to 0. We have no flux boundary conditions along 3 sides, and then one boundary condition for example, 3 conditions at 0. But yeah, if you have any expertise in this area or any ideas at all as to how to actually provide this,
to do the discrete, just do the generating function of the discrete.
Yeah, maybe.
Because the boundary conditions are easy to get accounted for. Okay, the last one is probably more.
Yeah, so Ellen and I looked at the discrete formulated for lipid structure modeling. I don't think so.
No, this is just going to be worse.
But it's first order P. I mean, if I look correct, it's first order.
And he did the sort of like single variable, just lipid structure, and there I think the asymptotic was more significant. Well, so in the process of doing that, we did look at the discrete equation steady state. We've got one variable, and it wasn't very nice.
Yeah.
So this is just going to be worse.
We derived
Because it's first order. Do the
Well, so-
generating function. It's just, I mean,
Yeah,
can you go back to
it's
the?
I guess if you can probably write down a generating function, but it's not very insightful. I think it's the problem.
Yes, I can show you. I mean, this is the at steady state, basically it's 0, and this is the upgrade equation.
Right. So that's all generating function. The first order, the phi and the they all gives you generating function there.
Yeah.
Yeah. So okay, so there is the last term which is we don't know. Okay.
Yeah, if I've got
Yeah. Okay. So
it just becomes ugly.
so it's probably the boundary condition, the last boundary condition which makes it harder. But yeah.
So that said, with just lipid structuring at steady state, we use generating function at steady state, and we could derive a closed oxidation. And it means okay, something. Yeah. I do think it is actually possible. I think you're right to actually do some big ones. I just don't think that it would be really insightful in terms of extracting information out of the company. But it is something that I consider looking back with.
Because I guess what you didn't say was with your post-mortem state, actually with that change in size, depending on the rate of fat, I mean that's the final determining parameter. And so I think you get more insight into why the distribution of the mean distribution of fat rate at steady state looks quite different because it's basically dropping to zero.
Yeah. Yeah.
So you get qualitative change, either profile is at one point you think that you increase sort of way around go, or it's one common. So you can get quite a lot of insight, which is not so apparent when you just did generation.
Yes.
Like,
Well, I mean, the other thing is, I mean, we didn't do too much digging into doing the generating content and then maybe converting it from the solution part, maybe it's a sterling problem.
Yeah.
That might be a productive way of looking at this stream and it's not from. But yeah, do you know if this would be straightforwardly solvable, for example, if this was just a constant and not depending on like prime L?
Well, I mean, I think it's the biggest complication is your boundary.
Yeah.
The last one, not the other. The other three, like it's the last one. It's a bit tricky when you're that. That one is just the heterogeneity. Not a big deal. I'm just give a special stuff. It's really the last boundary.
Okay.
So this is the results of the tyranny of continuous variable.
They're both good at something. But yeah, would be happy to talk about this a little bit more. So I think that's a good idea to look into the generating content a little bit here. And then I just wanted to change gears just a little bit to talk about the second project, the work I'm currently doing. So this is going to be really basically things. But here we've got phenotype and we're just looking at lipid structure and space. So space is a continuous variable now. So this is basically your macrophage domain. You have x equals 0 corresponding to the endothelium. So this is where the artery wall meets the blood flow. And then you have x equals 1, which is the next layer of the artery wall. All the dynamics are happening between x equals 0 and x equals 1. In terms of physical space, it's about 1/4 of a millimeter, we realized yesterday, actually. It's 1/4 of a millimeter wide, so it's very small.
So that's essentially that's a radial.
Yeah, that's right. Yep. But we're taking a really basic Cartesian approach to start. So x goes from 0 to 1 and content. As before, macrophages are recruited at the origin. So they come in with the minimal lipid content at x equals 0. And they go through a bunch of processes. So lipid uptake moves up, offloading down. What's different now is that we have diffusion. And what's tricky is that diffusion is lipid dependent, biologically speaking. Macrophages that have more lipid content are less mobile. And this is, I mean, it's kind of intuitive. They have more mass, it's just harder to get around. Lipid dependent diffusion and also lipid dependent depth. So these are the two things that we want to focus on with our modeling. Lipid is, generally speaking, toxic to the macrophages. They can't handle too much. So the more lipid that they have, the higher their rate of death. So I'm just presenting here the macrophage dynamics. And in particular, so there's lipid-dependent diffusion here, which is controlled by this parameter sign mobility, sign one. And there's lipid-dependent depth over here. And as I said before, basically diffusion decreases with L, and depth increases with L. Then the next line is uptake, offloading. This is recruitment, and this is F concept, x equals 1. So just really preliminary results right now. So I've run some numerical solutions just to see what happens as time goes on. So in each of these, we have states on this axis, and snapshots through time from left to right. And as you can see, as time develops, you have limited independent movement in depth. The steady state distribution is constantly at that development. So this is where they enter, it's unsurprising. But the distribution spreads itself all the way to x equals 1. So macrophages are actually traveling through and escaping out the outer boundary. Even another thing you can notice is that as you go deeper into the lesion, lipid content is increasing. This is also a little bit unsurprising because in order to get to the other side of the lesion, you have to take up lipid along the way.
The last one is a steady state, or it
Yeah.
doesn't work.
Last one is steady state. It's just time going from. So, what happens when you turn on the dependence movement? So basically, at steady state, the main difference is that you end up with an accumulation of macrophages with high lipid content deep inside the meat. And you can understand this intuitively. Macrophages have taken up on those lipid, and then they become less mobile, so they get stuck there. So the function of lipid-dependent movement in atherosclerosis seems to be to accumulate macrophages towards the deep parts of the meat.
Can you show that video that was comparing?
So it's just a bright spot. And then the other effect is lipid-dependent depth here. And what you can see is that it has a dramatic effect on the depth of infiltration of these macrophages. So the distribution now with lipid-dependent depth doesn't span all the way to x equals 1. It kind of gets top off the macrophages. So the function of lipid-dependent depth just based on how preliminary results seems to be that it affects the depth of the infiltration of so just to summarize, yeah, lipid-dependent movement promotes retention of lipid-laden macrophages deep in the meat. Lipid-dependent depth limits the depth of infiltration of macrophages. It's still an open consideration as to how to quantify these effects specifically. So I'll be interested in talking about that. But there is also another problem, which is considering the steady state distribution in the case of lipid independent movement and depth. So just the simplest situation, it would be nice to have some analytical results with which to compare the current results. In the continuum framework, this is the PDE that pops out. And what you have basically is, well, this thing is separable. Remove the spatial terms, this one and this one for the other side, and what's left is just the lipid terms. So this thing is spatial, is separable, but the issue is that this coefficient vanishes as L goes to 1. So that's one of the boundary points. So this is a separable PDE with I forget the word now. But yeah, you get a vanishing coefficient at the boundary. It's singular. And I'm having trouble actually separating these variables. So if anyone has any expertise in this, dealing with single problems, for separating variables, I'd love to run the problem by you. But yeah, that's roughly all I have to say. So thank you for listening. Yeah, if you have any questions.
Can you go back to the field in the space of lipid and phenotype, where you have the points of zero velocity?
Yeah.
The movement, what is time is the left to right?
Yeah, sorry, it's not the most intuitive.
No, it's okay. But I realized that the zero velocity point moves not monotonic. Does it mean anything for the development of people?
Yeah.
The curious.
Well, I mean, it tells you a bit about, so this is, you can interpret the linking points, kind of the target phenotype. So what it says is that the target phenotype and lipid content is changing due to changes in the microenvironment. And I didn't go into details about the microenvironment. But yeah, in general, what happens is this point actually starts out on the right hand side. So very early on, macrophages are put in the pro-inflammatory range. They always are. And then what happens is time to talk, this point moves left. And this happens because the microenvironment becomes more anti-inflammatory, and it's because of processes like atherosclerosis and stuff that I didn't mention. But in general, yes, the point travels from the right hand side, left, and then back up at steady state.
You want to explain because it's actually quite intricate in terms of in the phase marker now and age are actually all evolving in time, subject to ODs, which are related to how many phases there are in the domain. And so this is why that hit point is like moving around. So there's a sort of a scale dynamics right in the so it's actually quite
and it would be good to actually, I mean, I hesitate to say it's intuitive once you look at the extracellular dynamics, but it's understandable.
yeah, because you can see the fixed points for L and I, you can read them off and they got L and H and given that those are evolving over time. And you need to go back to later if there is a close up system. So it might do this. So get the number there and then
you can view this as a driven the S part of the S part is still the L and H but yeah, this accumulating points you can solve it by setting the left hand side.
Yes.
Yeah.
So it's a bit weird.
It's very good.
The second problem, you account for the role of the fact that lipid content affects macrophage death.
Yes.
What would happen in this? Could also introduce it and see how that affects this.
Yes.
This curve. It's something that is relevant.
It is very relevant to how it's working. So the problem is when you have lipid dependent or phenotype dependent behavior, the equations become much more difficult to analyze. You don't get, you get non-linear terms popping up even as leading order is, so it's very difficult to solve it. So what we're working on at the moment is we're looking at lipid dependent death and phenotype dependent movements and all sorts of behaviors. And we're doing a sensitivity analysis to figure out what these effects are, what impact they have on things we care about, like how much lipid debits in the actual lesion, how many macrophages there are, all of this at steady state, otherwise it's too hard. But yeah, long story short, very important, especially important to biologists, but it's great. Yeah. Yeah, of course. Yeah, so one of the effects is that, well, uptake, lipid uptake is dependent, for example, on the phenotype. macrophages that are anti-inflammatory take up lipid more easily than pro-inflammatory macrophages. So there's a phi dependence secretly in here. There's also a phi dependence in offloading, that's the other way. Pro-inflammatory cells seem to be better at offloading for some reason. Interestingly, there's also lipid dependence in phenotype population. So macrophages that have taken up a lot of lipid are more phenotypically robust in some sense. They don't respond as well to pro-inflammatory signals. And none of these behaviors are accounted for in this framework, right? We did basically the bare minimum to actually capture what was going on with phenotype and lipid and make things as analytically tractable as possible. What's really needed is a numerical study for the diving into next.
Do you know if the medication against atherosclerosis play a role in at this stage of the disease, or they are?
Yeah, so when you're thinking about therapies for atherosclerosis, there are two main things that sort of come to mind at the early stages. One is lipid therapy, so it's to reduce the amount of LDL in your blood, basically, statin therapy. And that's certainly relevant in terms of even at early stages. It affects, the amount of LDL, as we saw, affects how much lipid is inside the lead and how much contained in the macrophages. So statin therapy is very important in that early stages. Another type of therapy is SPM therapy, which hasn't been approved for in humans as of yet, but it's promising in animal models. Basically, what that therapy is trying to do is to modulate macrophage, so it affects this body. And I didn't mention this explicitly, but phenotype promotes recruitment, pro-inflammatory means more recruitment to some extent. What SPM therapy does is it tries to promote an anti-inflammatory phenotype. And so you're driven towards negative values of 5. We actually we looked into applying both statin and SPM therapy to these equations. But we decided that it would be best more systematically analyze the impact of both these therapies when we've accounted for all these lipid and phenotype dependent effects. Because maybe those lipid and phenotype dependent effects actually have a huge role in terms of, I don't know how therapies are affected by these effects. So that's going to be part of the next study.
Anything else?
Similar in the animal world. What would be a behavior that's similar?
I don't know if anyone's done work on it. There's people looked into microplastic in the pitch, for example. And that's sort of relevant when you're fishing eating it. You start accumulating microplastics, but it also affects fish behavior and that kind of thing. That was him thinking.
No, it's just confusing.
Going back to the question.
It might be sort of like a diet that animals
Yeah, they've never seen this sort of model. Yeah, the beat of the quality, what they correlate as the climate change or
Yeah.
So it's sort of more large scale, not not that.
But are there studies on the animal side? So
climate change is a lot with migration, range, migration range on the ecology.
Doesn't have to be the animal mass of the animal.
Yeah, yes, yeah.
Yeah. It feels like structured population to make the kind of a bit left out in the cell biology framework than in ecology framework. But it's certainly a flip in some lots.
Yes, in epidemiology.
Yeah,
And some models have many stages.
Yeah,
The way they affect the detection.
yeah.
You know,
Viral loading, for example, is another
thing with malaria.
but yeah, I think that's mathematically perhaps it's making more interesting to look at structured populations for cells because people have been looking into behaviors like cell division and that kind of thing. It doesn't really have to be scale. Interesting. Structured by mass still has something parts in cell division events. So that's just speculation as to why we have to go deeper in terms of ecology level structured population modeling.
okay,
Thank you.
thank you.